Hello and welcome to the Daily Space for Monday, May 22nd, 2018. I am Dr. Pamela Gay and I am here to put science in your heads. So today is a kind of slow news day. I think that everyone is starting to enjoy the fabulous spring that is currently happening in the Northern Hemisphere. And so instead of bringing you a lot about stars, galaxies, and exoplanets, I'm instead going to take you into the inside of atoms. There's been a lot of research going on trying to figure out just what is it like in the innermost core of an atom. We know that atoms consist of protons, neutrons, and electrons, and these protons and neutrons are built up of even smaller particles called quarks. In the case of a proton, we have two what we call up quarks and one down quark. Now, that doesn't mean the quarks are pointed up or down. It's just the names that we gave to these particular quarks. There's a lot of quarks out there, but it turns out all the regular everyday matter that you deal with is, I'm not quite pointing the camera at myself. Thank you so much, AstroHelg, for the bits. You guys are awesome. So it turns out that not everything that we deal with on a day-to-day basis is actually made out of just those up and down quarks. All stable particles are made of up and down quarks. Electrons, they're like stable by themselves. They're not made up of anything smaller. Well, in the case of protons, a lot of different theories have been working to try and figure out, are protons stable or not? This allows us to start to figure out how our universe will end. It allows us to start to figure out, is there a grand unified theory of all of the different forces? Basically, a lot of different theories rest on the stability of the proton. And one of the things that people needed to understand the stability of the proton was to understand what's going on inside this particle. We know that these two up and one down quark are held together by the strong nuclear force. And the question has always been, what exactly is the pressure inside this conglomeration of three little tiny particles? And it was thought since the 1960s that we would never be able to measure that pressure because how? It's this little tiny thing smaller than any detectors we have, and we couldn't figure out how to get there from here. But with recent theories, people realized while gravity is an extraordinarily weak force, and you can generally completely ignore it within the context of particle physics, it turns out that if you make careful enough measurements and you combine a couple of different physical frameworks, you can shoot high energy electrons at a proton and measure the scattering of the photons that come off. And using this combination of Compton scattering and gravitational frameworks, gravitational form factors, you can actually get a handle on what is the pressure if you could get inside between those three little quarks. Now, what was amazing and what blew up the internet yesterday afternoon when this news came out is that the pressure inside the proton, if you could be inside the proton, what you would be subjected to is 100 decillion pascals. That is a 1 followed by 35 zeros. And for comparison, our own atmosphere is only 100,000 pascals. And this is 10 times the pressure that we have inside of a neutron star. Now, the question that many people instantly had on hearing this news yesterday was, well, if this is the pressure inside of a proton, do we still actually understand the pressures inside of a neutron star correctly? Why is it that the pressure inside of a proton can be so great? Well, when we're looking at what is the supporting factor of a neutron star versus what is the pressure inside of a proton, we're actually discussing two totally different kinds of physical processes. within a normal white dwarf star, where you have a sphere of protons that is swimming with a electron degeneracy pressure of all of the electrons, making sure that no two spin ups share the same energy level, no two spin downs share the same energy level, so that the Pauli exclusion principle is always followed, and you always have the one up, the one down, and all the shared energy levels within the white dwarf. What we're looking at here is not the crushing of an individual proton. What we're looking at instead is if you put enough pressure onto this white dwarf by increasing its mass, increasing its mass, increasing its mass, until its mass is so great that the protons, which are pushing against each other, can no longer hold each other apart. That is the point when the protons and the electrons with the it's actually the electron degeneracies that we're worried about. When these individual particles can no longer push each other apart, the smashing together of these particles is what causes the electrons and the protons to combine to form neutrons. So it's not that we're breaking up the pressure inside the proton. It's actually that we're trying to pack things so closely together that the electrons and the protons have to combine into neutrons. It gives off a lot of energy, creates a fabulous nova. And no physics is harmed in the process of making this discovery of just how dense the inside of a proton actually is. Now, it turns out today's news is littered with particle physics. In news coming to us from Italy, a scientific experiment that literally reached across national borders has finally shown us quite definitively that muons, well, not muons, rather neutrinos, have a rather horrible habit of changing identities. It was long known that there was something weird going on with neutrinos. When we try and observe the number of neutrinos coming off of our sun, the number of a specific kind of neutrino that we were able to detect was significantly lower than what all of our theories predicted, which told us that either our understanding of the sun was very wrong, or neutrinos are instead doing something very different than what we expected. As recently as the late 90s, we didn't know, do neutrinos have mass? Are they massless and capable of moving at the speed of light? We had a whole variety of questions that all started to make more sense when we realized, yes, neutrinos have mass, and as a result of having this mass, they're able to shift their mass into energy, or shift their energy into mass, and thus switch identities. The electron neutrino is the lightest weight of this family, and if you have an electron neutrino zipping through space, it can say, I'm going to zip a little bit slower and become a muon neutrino, which can also say, I'm going to travel a little bit slower and turn into a tau neutrino. The way that we figured out definitively that this is happening is CERN is able to generate neutrinos, and there's a detector across the border over in Italy. So here we have CERN, which is spanning the border between France and Switzerland, producing neutrinos. And the way that it does this is it pulses a beam of protons at a lead target, and every proton that hits the lead target is able to shoot out 300 neutrinos from that lead target. These neutrinos then go flying across our planet, and some of them are detected in the facility in Italy. Over the years that this has been happening, they've now been able to detect 10 muon neutrinos. Now, that may seem kind of sad when you've detected so many neutrinos that you can actually start to name them after characters in your favorite sitcom. But it's really hard to measure neutrinos. It turns out neutrinos are one of these kinds of particles that prefer not to interact with other atoms with other particles and atoms. And instead, they would rather just pass through without saying hello or changing anything's state. you can, if you're unfortunate, have a neutrino pass through an entire light year of lead without ever interfering with anything and giving away its presence. This means we only are able to detect the smallest fraction of the neutrinos that are produced. So detecting those 10 muons sounds kind of, well, like a low count, and it is a low count. But for what we're doing, it's an amazing count, and it confirms our physics. Neutrinos like to change their clothes, and wouldn't it be nice to be able to change your mass just by running a little bit faster or slower? So, in further news, we have news that actually is going to be even better news, hopefully later today. This afternoon, out at California's Vandenberg Air Force Base at 12:48, basically Pacific time, there is going to be a launch of a Falcon rocket from SpaceX. And this particular Falcon is going to launch the dual satellite Grace follow-up mission. Now, when I say dual satellite mission, it's as simple as the way it sounds. This is two spacecraft that, working together, are doing one mission to study our planet Earth. These two particular satellites, they study the gravitational pull of our planet on these satellites. And by traveling in tandem around our planet and maintaining contact with one another, they're able to see slight deflections in each other's orbits that are caused by differences in the material inside of our planet. A difference in density from one place to another can be indicative of many different things. We actually were able to find, well, not me, but scientists who were out looking for oil in the Yucatan Peninsula were able to detect the places in the Earth that had been crushed into a significantly higher density by the impact that killed the dinosaurs. It turns out, by moving along with a gravity sensing device, you can detect there's oil underground, there is crushed something underground, there's a hollow space underground. Or if you're the Grace follow-on mission, you're able to follow the water on our own planet. It's one of these fabulous features of water soaking into our world that it actually changes the gravitational pull from one place to another. If you're living in California during a drought, you may detect that you weigh a little bit less than you seem to weigh during a rainy season when the ground is denser with all of this underground water. So the Grace follow-on mission is going to follow up on where the water is inside our world. Now, in addition to the Grace mission, this Falcon launch is also going to launch a series of Iridium satellites that are used for satellite communication. These both sets of satellites, both Grace and Iridium, had previously been slated to launch on two different Russian Dnepr rockets. Now, due to unfortunate political circumstances between our nation and Russia, these missions had to be launched on a new spacecraft. Now, because the Falcon vehicles are able to launch significantly higher weights, or higher masses as the case may be, than the Dnepr rockets could, they were able to share a launch vehicle. So where it used to be two launches on a Soviet mission or a Russian mission, we now have one launch by one, well, spacecraft built by an American entrepreneur who was born in South Africa. And this is going to be one heck of an international mission. The Grace is actually a collaboration between NASA and the German Research Center for Geosciences. And Iridium, well, it's an international corporation. So here we are, truly starting to move into a new commercial space future where we have individual corporations launching off of military and civilian launch pads, launching missions that are founded by people all over the world. Now, should this mission launch successfully later today, we will bring it to you live right here on Twitch. Starting about half an hour before launch, we will be going live. We will be hosting over the NASA TV stream and providing commentary on both the satellites and the science that goes along with them. So come back later today and learn all about these amazing missions. Now, this has been your Daily Space. If you liked what you see, give us a follow. Follows are free. If you want to sustain the show and keep seeing it into the future, every subscription and every bit helps. This show is a production of CosmoQuest, and we are brought to you by the Astronomical Society of the Pacific. Our job is to put science in your brain. Now I'm going to turn over to the chat and work on answering your questions. Thank you. So, folks, what do you have for questions for today? I wouldn't say a neutrino is gender fluid, Larry. I'd say it's identity fluid. I'm not sure genders exactly apply for quarks or any other, not quarks, for neutrinos. So I see Larry asking, do the down quark side of a proton has... So quarks individually have fractions of a charge, and it's in adding up the 2 up and 1 down that we're able to get to 1 positive charge on the proton. So with fractional charges, everything gets a little bit more harder to calculate. So do we have any other questions? Hello, Michael. Hello, Peter. Hello, Bill. Hello, K. Brouk. Hello, KB. Hello, Bill Wink. Hello to all of you out there. I'm looking to see if we're going to have any more questions and seeing what all is going on out there on the feeds. So Peter is saying no allergies today. Well, I'm still having some allergies. So any of you who were here yesterday know that I actually ended up broadcasting with sunglasses. This is because I have an allergy to latex, and I keep finding it in unfortunate places. I was using some glue the other night and got it on my hands and rubbed my eye with a little bit of the glue on my fingernail, and my eye just like was massively swollen yesterday, and I'm still a little bit red, and it's a no makeup kind of allergy day, but I'm doing much better, thank you. So Larry is asking, which forces are in play with an internal protonic pressure? This is the strong force. So the strong force is what's holding these quarks together. It is the strongest of all of the forces, thus the name, the strong force. Hello, keeper of maps. Thank you for your sympathies, KB. Somewhere in here, I have more windows. There we go. So for those of you who are new and want to learn more about this particular show, and thank you, Tobatij, for the follow. Thank you, Stormbringer29 for the follow. And again, thank you so much, Astrahelge, for the bits. That really helps. Yeah, allergies are just the worst, Peter. So the Daily Space is a new show we're going to be bringing you every Monday through Friday, same channel, same time. It will be hosted by myself or by Dr. Andreas Plazas, who is one of our new scientists here at CosmoQuest. And hello, Big J. So our goal is to review the news each day so that you don't have to hit on what are our new understandings, what are the things to pay attention to. We're going to periodically on Mondays bring you bigger in-depth looks. Next Monday, I hope to be bringing you an in-depth look at all of the science that has already come out of the Gaia Data Release 2. And the rest of the time, we are at the whim of what the peer review system allows to be published and What new press releases are coming out? Um, so I see Henny's Vorverp is asking what causes the pressure. Um, so yes, virtual particles are at play. There's always bosons in the mix. In this case, it's the W bosons. I think it's the W bosons. And the way really to think about it is the strong force is holding these quarks together. And just like if you have two magnets and try and pull them apart, you have to exert a force to do that. And there is a force holding those two magnets together. With the quarks, there's a force holding the three quarks together as soon as they get close enough together to be latched on by the bosons. So the bosons are mediating the force. The force is the strong force, and the force that we're talking about, the pressure that we're talking about, is inside these quarks. And I'm going to have to double check which boson it is that mediates the strong force, because I'm having a moment of, I'm not sure I'm right. It is the gluon. I was wrong. Sorry. Neutrinos are mediated. The neutrinos changing identity. I'm mixing my science for the morning. The neutrinos changing their identity. The story that we talked about with the neutrinos flying from CERN over to Italy and changing their identity. That is mediated by the W bosons, and the protons and neutrons are held together by gluons. Thank you, everyone, for chiming in. So Bill, a good scientist is always willing to say, I don't know, and always willing to say, let me look this up, especially before their second or third cup of coffee. I've had two, I haven't had three. After three, I can remember my bosons a little bit better. So the available energy levels, Michael, is more for where the electrons are. So with the electron degeneracy pressure, we have essentially all of the protons within a white dwarf, and I'm oversimplifying here. They're essentially sharing the electrons between all of the different protons, and with this degeneracy pressure, it restricts what energies the electrons are allowed to have. So it's with those available energy levels that we end up with the electron degeneracy pressure. With quarks, it's a little bit more complicated. Oh, Peter, I used to grab the pot of coffee, and then my husband cut me off and got us a Krups because he knows I worry about the environment. And so instead of going through more of the K-pods, I drink less coffee. Okay, do we have any other science questions out there? Okay, so Uncle Bill is asking, please remind me the difference between the strong and the weak nuclear forces. So the weak force is what's involved in things like beta decay. So it's basically when things change identities in different situations. This is where you start seeing the weak force involved. The strong force is what gives different particles their individual identity. Right now, I shall be this proton, and my quarks are glued together with these gluons. So think of the weak force as the thing that gives people, or not people, gives particles their weak identities. And the strong force is what binds together the particles. So Hanny's Vorverp, the pressure inside a neutron star, like I said, these are two different kinds of situations that we're talking about. The pressure inside the neutron star is the pressure between two different neutrons. And if you get two neutrons so that you overcome the pressure that's holding them apart, the neutrons will collapse down to form a black hole. And we don't actually know what the constituent matter of a black hole is. So with the neutron to neutron pressure inside of a neutron star, that's supporting the star outwards. The pressure inside of a proton is holding that proton together. Um, if you overcome that pressure, it's just a different thing that you're looking at. One is supporting a star, the other is holding together the proton. I don't know if that helped. Um, so Michael is saying, so do you have any idea what happens when a neutron star gets too massive and collapses into a black hole? Um, I know that physics breaks at the event horizon, and we just can't tell you. Is a black hole a point source? Does it have a finite radius? We just don't know yet. Um, Larry, in order to give you a coherent explanation of the color force, I'd have to go back and review my particle physics. It's been a long time since I looked at that. So why don't you send in, or actually, we talked about this in an astronomy cast. So I bet if you go digging through our astronomy cast archive, you'll be able to find the one where we talked about color. Um, so Michael, you get the neutron star by squishing the electrons and protons together. What happens in this case is the proton and the electron are held apart with it's part of the electromagnetic force, and when you overcome the unwillingness of these two things to come together, you end up with I'm going to just jumble this. You guys are trying to go, and I commend you for this, further than my particle physics is allowing me to discuss on the fly. Why don't I, today's Tuesday, why don't I on Thursday, when we don't have Matt's office hours following up, I will do an overview of particle physics once I make sure it's fresh in my brain. Because you guys clearly are deeply, deeply curious about this. I will go over all of this on Thursday. Bill, there is no theoretical maximum size for a black hole that is dictated by physics doesn't allow it to get bigger. There is a maximum size based on if the black hole is trying to form in the center of a galaxy, it will end up turning itself off essentially. That is a different thing that I'm going to put on the list of things for us to discuss on Astronomy Cast. Basically, how a black hole can starve itself out of future growth. Okay, do we have any other questions? And as I said, I'll come back Thursday after I review particle physics, and hopefully things will go a little bit smoother. I actually have 2 more minutes, and then I have another meeting. So type quickly. No, our universe is not a black hole, Larry. I'm just going to nope that one right here. Any other questions? Yeah, Michael, I have to admit, I have done particle physics much more recently, but it's one of those things that unless I keep doing it, I just lose the little tiny details. Yes, you guys are awesome. Okay, so I am going to review my particle physics. I will come back on Thursday. Bring your questions back. We will be doing Daily Space tomorrow at 1 p.m. Eastern, which is 6 p.m. England and 10 a.m. Pacific. I will be here with, more news from the world of astronomy and space science. But before that happens, if all goes well, I will be coming on later today at about 12:30 Pacific, which is 3:30 Eastern, to provide commentary for the launch of the Falcon carrying Grace follow-up mission and a set of Iridium spacecraft. So wherever you are in the world, go look at particle physics. It's hard. And have a fabulous morning, evening, or afternoon. And remember, keep looking up. Bye bye.